Hello and welcome to the Cisco Support Community. Today we present a live Cisco Support Community Expert Series webcast event. And during our event today, the topic will be 802.11 frames, an in-depth overview with Cisco VIP George Stefanick. My name is Francine Richards, and I'm the Web Marketing Project Manager for the Cisco Support Community. Our expert joining me today is George Stefanick. George is a wireless architect employed by Houston Methodist Hospital System. George manages a large and complex wireless network that includes more than 2,500 access points and upward of 11,000 concurrent Wi-Fi clients. George has been in wireless communication since 1997 and holds various vendor and vendor-neutral certifications. He focuses on high-density indoor deployments in the healthcare vertical, thereby using his hands-on experience in site survey, RFID, and voice design. As a consultant, George has consulted with Fortune 500 companies using his real-world hands-on experience to meet the needs and challenges in today's enterprise environments. George is a Cisco Support Community VIP for 2012, 2013, and 2014, along with the Aruba MVP 2014. Welcome, George.
Hello there. Joining
George today is Nicola Darsha and Bernardo Gaspar. Nicola is a wireless and authentication authorization and accounting expert for the Technical Assistance Center at Cisco Europe. He has been troubleshooting wireless networks, wireless management tools, and security products, including Cisco Secure Access Control Server and Cisco Network Access Control since 2007. He also focuses on filing technical and documentation bugs. He holds a bachelor's degree in computer networking and a master's degree in computer science. He also holds CCIE wireless certification 25344. Bernardo is a customer support engineer at the Technical Assistance Center at Cisco Europe, specializing in wireless and authentication, authorization, and accounting. He has been troubleshooting wireless networks, wireless management tools, and security products, including Cisco Secure Access Control Server, NAC, and Identity Service Engine as part of the escalation TAC team since 2007. He also focuses on filing technical and documentation bugs. He holds a degree from the University of Porto. Now, I'd like to briefly outline the format for today's Expert Series webcast. George will start with the presentation and demo for the first 60 minutes of the program, and then we'll dive into the live question submissions for the remainder of today's event. During our live presentation, you may submit questions to be answered by George and the team of Cisco technical experts using the Q&A box on the right-hand side of your console. The team of technical experts is well-versed in 802.11 frames, so please begin posting your questions now to give them the best chance of answering them. And also, if you experience any technical issues, please post your question in the chat. We'll be asking polling questions during this webcast, and we highly encourage you to participate by answering them. You may download a copy of today's PDF presentation using the link in the chat window. And now let's get started with today's event. We're going to start off with a polling question for the audience. How many of you are familiar with capturing 802.11 frames? A, yes I am, or B, no I am not. So take a moment to answer that, as this will give our experts an opportunity to tailor the presentation to your needs. Make sure to submit your questions, as we'll answer them a little later in the webcast. And now I would like to hand the mic over to our expert, George, who will start the presentation.
Excellent, thank you. And welcome everyone. Again, my name is George Stefanick. I'm a wireless architect for the Houston Methodist Hospital System. I've been with Houston Methodist for about 5 years. Prior to working at Houston Methodist, I worked for a Cisco partner focusing on mobility. Again, as mentioned earlier, I have vendor and vendor-neutral certifications. I blog at my own blog site, my802.11.com. I also contribute to the No Strings Attached show. I am a Cisco VIP as well as a Aruba MVP, and focus on consulting, doing training, site survey, deployment, and troubleshooting. Now, in this series, I'd much rather a whiteboard. However, I think most of you will find the slides informative and contain very rich content. During my slide presentation, I want to challenge each of you. If you can take 2 or maybe 3 things away from my presentation today, then I did my job. So if you can, there's a lot of detail. If you didn't know something in my presentation and that you know now, that's great. Also, as a Cisco VIP, I spend a great deal of personal time answering questions. And with that said, I personally define my own success and how I can help others on their journey to Wi-Fi. I'd like to personally thank Nicola and Bernardo for assisting on the answers and questions. And a special thank you to two people that I call friends who've guided me through my experience of 802.11, Andrew Von Neggi and Marcus Burton. And last but not least, I'd also like to thank Sean Jackman, who instilled fundamentals in me early on. And ever since learning Wi-Fi, I never worked a day in my life. And in closing, the gals over at CSC, Lisa, Francine, and Monica, really appreciate your help. So a little bit about our infrastructure. We have 9.5 million square feet. It includes a research institute, 7 local hospitals. We also have 10 towers in the Texas Medical Center. The Texas Medical Center is coined as the largest medical center in the world. We have approximately 1,800 beds, 15,000 employees. Our inpatients are just over 81,000. Outpatient visits are over 500,000, and our ER visits are about 250,000. So it's a rather busy institution. A little bit about our infrastructure here at Methodist. We have 8 wireless distributions. Inside those 8 wireless distributions, we have 14 WISM 2s, 4 5508s. We anchor our guest traffic as well as our office extends to 2 5508s. We have approximately 11,000 concurrent clients, and of that, 20% are voice clients, a mix between Cisco 7925 handsets and 400 or so Vocera badges. We're just now reaching about 3,000 access points in our deployment. We have a large deployment of Cisco Office Extends. We leverage Cisco Prime, Cisco ICE, Cisco MSE, and all of our outlying facilities are location grade, with the exception of our downtown, which we're working on for next year. And last but not least, and something of important interest, is our all wireless office, AWO, as we call it. And we'll be commenting later on in the presentation about AWO. A little bit about the devices that we support. It's rather challenging. When you work in a medical facility, you see all kinds of devices, mobile robots, in fact, and not only the voice devices, but EKG carts and Cisco telepresence, mobile ultrasound carts. And at Methodist, we go through a very strict testing process. So we've partnered with Biomed Facilities and Security, who give us lead-in to products that they're interested in. So rather than doing a purchase and then, oh, by the way, you need to make this work in the wireless, we try to get in front of that. So we have a very strict testing policy. We look at how the clients hear, how they interact with noise and interference. We see how they roam. Do they provide or support opportunistic key caching, or FT 802.11r, or PMK cache? Are they sticky to an access point? We try to understand all these things ahead of time before we do the purchase, work out those kinks before we actually put them on our network. Long term, it saves money. So a little bit about our agenda this morning. We're going to be talking about management, control, and data frames. Then we're going to be jumping over to how a frame and packet and bits move through the network. So we're going to be looking at the LLC, the MAC, the PLCP, the PMD layers. And then we're going to jump over to how to capture 802.11ac frames from a Cisco access point, and an update on our all wireless office. Now you're going to notice that carrier sense multiple access collision avoidance is scratched off there. When I started doing the slides, there was just so much rich content that I was going to go over my hour. However, I did add a slide or a conversation piece about carrier sense multiple access collision avoidance, so hopefully not to disappoint. So first on the agenda here is management and control frames. What you're looking at here is the backbone of Wi-Fi. Management, control, and data frames is what goes on the wireless network. Management frames are the fundamental practice of radios communicating, how they detect the network, how they join a network, how they operate on the network. So you see some of your basic management frames, your beacons, your association requests, association response. And control frames. Control frames facilitate data frame delivery. They act like traffic cops almost on the Wi-Fi network. And then data, you're going to notice that it's simple data. It's a payload. Now, something that I think is important and I want to mention is that you see a lot of frames that have CF in front of them. That is actually contention-free frames. And to start it off right, let's go back to when we had Beta and VHS. You had two competing standards, and VHS won out. Well, PCF, which is point coordination function, and DCF, which is distributed coordination function, were very similar in that they were two different standards. PCF was more point coordination, whereas an access point would direct the client. Do you have any data that you want to send? And then pull to the next one, and then to the next one. Think of a token ring almost. And then you had distributed coordination function, where it's a contention period where clients use carrier sense multiple access collision avoidance, where they will interpret the network whether or not they should transmit or not. Well, PCF never took off. So while you will see these frames in the 802.11 standard, it's very rare that you ever see them in the real world. In fact, if you ever do a packet capture and you do see the CF frames, it's more likely a CRC. It's not an actual frame that you captured or a correct frame. So when we start talking about frames, there's some things that we need to level set, and more importantly, you know, layer 2 frames are not encrypted. So anyone with the right tools and in range of the transmission and on channel can interpret those frames. So with the right tools, someone can easily eavesdrop on a network. Wi-Fi DOS attacks are easily achieved on layer 1 and layer 2. On layer 1, you just simply jam the frequency. On layer 2, you're seeing all the frames, and that's what we're going to be going through in the next 2 slides, of all the information that you can actually garner from a simple packet capture. Now, there are ways to secure your network, meaning MFP, management frame protection. Keep in mind that doesn't encrypt the actual packet, but what it does do is you can prevent clients from incorrectly getting deauthentication frames from attacker. And also, the encryption secures layer 3 and up. So we're going to be looking at an encrypted frame and a non-encrypted frame, so you can actually see the difference. But first, before we jump into the beacons, you know, I love real-world experience. And I'm going to give you a minute or two to digest this slide. And this is a real-world, out of my archive, packet capture of a complaint where they're saying the wireless is slow. So I'm going to give you a second or two and look at this packet or look at this frame and kind of see where you might find an issue. Actually, the issue in this frame is the retry rate. You're going to see here the retry bit is actually flipped to a 1, and the majority of the frames that we were capturing had this retry bit flipped to 1. And what happens is, imagine for a moment you and I are having a conversation, and all of a sudden, every 5 seconds, a horn goes off in your ear. As I'm having this conversation, you're going to say, "Hey, George, can you say that again?" And that's exactly what's going on right here. The bit error rate increased on the client, whereby the frame was not calculated correctly at the receiver, and it said, "I didn't get it." So it responds back with the no acknowledgement, and the sender then sends a retry frame. Here's a second world example. Again, slow network, right? I'll give you a few seconds. Let's take a peek at this one. Actually, the nav timer, the duration timer was 18,800 microseconds. Now, because I think it's important, let's chat a moment about the nav timer. Since I asked the in-depth carrier sense multiple access collision avoidance, I don't want to disappoint the audience who might be interested in that specific topic. First, I need to mention that this is very complicated stuff, guys. So follow along with me, and I'll go slow. Now, this is recorded, so we can always go back and reference if need be. First, carrier sense multiple access collision avoidance has 2 mechanisms. It has CCA, which is clear channel assessment, and it has NAV, network allocation vector. And what you're looking in this frame right now is NAV. So CCA operates on layer 1 on the spectrum, and NAV operates on layer 2, which is the MAC. Again, that's the slide that you're looking at. CCA, layer 1, the clear channel assessment, listens for a few things. It listens for energy detect, which is raw energy. It also listens for PLCP preambles and PLCP headers. And really all they are is simple zeros and ones. Now, there are a number of different preamble types. The most common preamble people are familiar with are long and short preambles, but there are many more, especially when you get into HT 802.11n and VHT, very high throughput 802.11ac. Now, preambles are used to synchronize a radio with an incoming transmission. The actual preamble itself contains two fields. It contains a sync field and a start frame delimiter. Both of these fields pretty much prime the radio for the incoming frame. The PLCP header is used also to determine the length or amount of time the pending frame should take to transmit over the air. This alerts the radios how long the frame should take to transmit. In other words, if you have an access point, before it sends the frame, the actual frame that you can sniff in a trace, it sends a series of bits of zeros and ones which represent the PLCP preamble and the PLCP header to prime the radios on channel of the incoming transmission. By the way, you can't sniff the PLCP preamble or PLCP header. You're kind of taking a leap of faith that vendors are implementing that properly. After the PLCP preamble and PLCP header are transmitted, the receiving radios ready themselves for the beginning reception of the actual 802.11 frame. After that frame is transmitted, all the radios in earshot of that transmission bring the frame in. These radios have no idea if that frame just transmitted is for them or not. Each radio demodulates the frame at the PMD layer. It sends it up to the PLCP layer and then to the MAC layer. At the MAC layer, the radio peeks at the MAC address and sees if the frame is addressed to him or not. If it is addressed to him, the frame proceeds up the stack. If it is not, the client will actually discard the frame. But before doing so, it looks at this nav value, the nav value that you're looking at this slide. The nav value represents the amount of microseconds a radio should go busy for the transmission that's currently in progress. In other words, the radio in which the frame was intended for needs to process the frame and acknowledge back. And that's just one example of why you would have the nav timer. So what's up with a nav timer at 18,800 nav seconds, microseconds? In fact, this was a bug on the Cisco handset. Many of the handsets were actually sending these particular frames with very large nav timers. Your typical nav timer you're going to find is anywhere between 40 and maybe 400 or 500 microseconds. So you can see when this frame got transmitted by a handset, all the clients backed off, which then resulted in a slow network. Again, another real-world example where packet captures outweighed a typical debug or a log or a GUI. This is where the rubber meets the road. And our last real-world experience before we get into the frames out of my archive is, again, slow connection. Story of my life, right? So when you start to sniff packets, you become very good at looking for problems, especially if you start to sniff packets on a network that is working. And then all of a sudden, when you look at frames on a network that isn't working, they kind of stick out like a sore thumb. This particular capture is from a device. This device is a medical device with a Netgear USB stick. And I'm going to give you a second to take a peek at the frame here and kind of get an idea or guess what might be the issue. Slow connection, application not working. What you're going to find here is the client device is actually sending probe request and null data frames. Well, we know null data frames have a very specific function. They actually go to the access point and tell the access point to buffer frames because I'm going off channel. Now, a client will go off channel for one of two reasons, either to side scan to build a neighbor list, which this is doing, or it will actually go to sleep, where you can actually save some battery life. The packet capture that we're seeing here is that the client is actually building a neighbor list. Now, something to note in this. On the right-hand side, you can see the USB stick surrounded by metal and then with a back cover of plastic covering the USB. It's not a very ideal situation. Even under the access point, the RF was so bad that the roaming algorithm was triggered by that client to just try to find another AP. And if you're off channel and you can't send traffic, that means now you have a slow connection, right? And that's what this guy was doing. He was trying to find another AP, even though he was right under it, because of the unideal situations that this was in. So a lot of probing. If you look here, you're going to see a lot of channel scanning. Bear with me a second. You're going to see here we have channel 11 scans, channel 6 scans, channel 1 scans, channel 11 scans, lots of probes, lots of probe requests, and our null frames. And you're going to notice the null frames are on channel 11, so this tells me that this particular client was actually associated to an access point on channel 11. He then went off and scanned channel 6, channel 1, came back to channel 11 and said, hey, do you have any packets for me, AP? And then if there were, packets were transmitted. So that's why I think it's important to understand how to interpret frames. Now we're going to look at a beacon. What is inside a beacon? A lot of rich information, and again, this is all unencrypted. You're going to see we have the SSID information. We're going to see we have the data rates. We have the TIMs. We have some QoS information, ERP information, and some vendor-specific information. So let's peek at some of that, shall we? So on the left-hand side, you're going to notice here we have a Cisco setup with an SSID as broadcast. Our SSID is called lab. If we were to sniff this frame, this beacon, you're going to notice right here under our SSID, we actually have lab. On a Windows device, you'll see that you have your bars and with the network name called lab. Now, when you turn off or you never turn off the SSID or the beacon, but when you hide the beacon by not broadcasting it, you're going to notice here that the SID is empty. In fact, you're seeing a dot here. I actually questioned OmniPeak on that, and we believe that that might be an issue perhaps in how OmniPeak is interpreting it. Maybe so, maybe not. Normally that's blank. But then you can also look at how Windows interprets a SSID that's not broadcasted. That's that other network that pops up. So a lot of wealth and information in a beacon. Next, you're going to look at the beacon also has our data rates. On our wireless LAN controller, if we go into our wireless tab, we can configure our data rates. In this case, this is actually in my lab, and best practice is not to enable your lower data rates. Of course, if your design supports it, you want to shut those off. But you're going to notice here, if 1 megabit, it's mandatory. So if we follow the arrow down to 1 megabit, you're going to see that the basic set, the BSS basic set rate is actually mandatory. The second one, 2 megabits, is supported, and you're going to see here that it's not a BSS basic rate. And then 5.55 is mandatory, and you can see here that it is set as a basic rate. So effectively, we can see what the network is actually supporting right from a beacon. Also, we have the beacon interval. So, again, I really love the geek stuff. Beacons are transmitted in intervals called TBTTs. It's a target beacon transmission time. It's defined by the .11 beacon period parameter in an AP MIB. All 802.11 device clocks count on kilo microseconds. That's right, kilo microseconds, in units of 1 kilo microsecond each. I mean, we're talking about very, very defined times here. Now, due to math, in the powers of 2, the 100 microseconds, the 100 millisecond beacon period you see in the controller on the right actually translates to 102,000 microseconds, which translates to 102 milliseconds. And also you're going to notice here that OmniPeak is saying that this is microseconds, but if you were to actually open up this tab, this frame would open up and you would see that these are actually milliseconds. So again, I often have that question, hey, I have a beacon interval of 102, but why is it 100 here? Again, because of the math. Now we're going to get into some good stuff. This is where I really enjoy reading packet captures. What we're looking at now is the beacon, and this is showing our Cipher and our authentication key management. This is an RSN information element, and you can see here in our wireless LAN controller we have WPA2 and AES checkboxed. So if you were to sniff this frame, since it's WPA2, it's 802.11i, it provides the RSN information element. The standard tells us that CCMP is the encryption of the cipher of choice, but however, TKIP is optional. But again, just from the beacon, I can see what security a wireless network is supporting. For example, we have the group Cipher, which is using CCMP. Now, what's important about the group Cipher, and I think it's very important to mention, not a lot of folks realize that multicast and broadcast traffic are encrypted differently than your unicast traffic. In fact, if you go onto the controller, you'll see this GTK randomization, for example. That's what this is. You can actually change that rotation key. All clients on the access point share the same group cipher, so they're sharing the same key. Pairwise, though, however, is a very unique association between two radios, in this case, the client and the access point. And this, my friends, is the cipher for unicast. So this is a very unique cipher. But you're going to see here that we do CCMP on the group and CCMP on the cipher. Also, here's the breakdown. If you were to see these others, 000FAC01, that means it's WEP 40. WEP 104 is 05. 03 is TKIP. 04 is CCMP. And again, you can see our 04s right here. Also, on the authentication management, we have two, 802.1x and pre-shared key. If we see 01 in our packet capture, that represents 802.1x. Now, the beauty of OmniPeek, it actually kind of breaks that out for us, right? That's why you see these hints here as you go through this. So again, a lot of information on the beacon. Now, let's take it a step further. Who has ever configured security and allowed all of the wireless security adoptions, WPA, AES, TKIP, WPA2, AES, and TKIP? In my experience, not a good thing, because some clients, when they see this, they just kind of nut up. They don't want to connect. Other clients, not a problem. For example, the Cisco phone, when it sees this, it actually negotiates to the highest. Other clients, not so much. But let's look at this. Let's look at a parameter, and this is two slides because we're going to be looking at the RSN information element, and our next slide we're going to be looking at the WPA information element. So this slide is focusing on WPA2 policy, and we have AES and TKIP checkboxed. So if we look at our group cipher, you're going to notice that it only has one cipher, and that's TKIP. Now you might be questioning, well, wait a minute, I just checkboxed AES. Why should CCMP be in there? Well, the fact remains is that if this network supports both TKIP and CCMP clients, and remember that key is shared for broadcast among all of the clients on that radio, well, TKIP clients can't understand CCMP traffic or their cipher. So it always negotiates down to the lowest common denominator for group cipher, in this case TKIP. But now if we look at our pairwise, clients can either do TKIP or CCMP on this network. Right? A lot of good information there. Also, we know we're doing 802.1x. We have the 000FAC01, which translates to 802.1x. Now, same beacon, just a little bit lower down, you're going to notice that we have a WPA element. That WPA element is because we've checkboxed that in our wireless LAN controller. Again, our multicast and broadcast cipher, and here you can see the WPA element is naming this separately here. It's actually spelling out multicast is TKIP because, again, we have both ciphers supported. It's downgrading to the most common one. And you can see our unicast ciphers are TKIP and CCMP. Again, a lot of rich information you can get from a beacon. Some other information you can get there are the Cisco proprietary and vendor-specific information. In this case, you're looking at, or have you ever opened up an analyzer and it says the name of your access points? Where's that coming from? It's actually coming from the beacon. You can see here under the Cisco proprietary the AP name. Some applications will detect that beacon and fill that information in, and also how many clients are actually on that access point. Also some DTIM information and country information. Again, very rich information in the beacon, as you can tell. You can actually tell what model the access point's configured for. If you're familiar with Cisco access points, you're going to find that a lot of those access points, you buy them by country code. You can't flash them afterwards. You can tell this access point happens to be an access point with the country code of US. And also for our DTIM period, in the Cisco controller, you can see where you can configure your DTIM and how that translates over to the beacon. Now this one's particularly interesting, and I want to spend a minute on this. For those of you that have Cisco phones, if you ever put it into a site survey mode, what you're going to find is that you actually have the RSSI value, and you have this thing called CU. That CU stands for channel utilization. Now, mistakenly, when I first started in wireless, I thought that went from 0 to 100 until one day I seen it at 125. Had to do a little research, and I realized this actually works on a bit scale from 0 to 55. But you're probably wondering, well, how is the phone getting this information? It's actually getting it in the beacon. The beacon is translating based on its time, its carrier sense that it's doing, and its secret sauce, how much the channel is actually being used. Now, if you do the math, you're going to find that this doesn't equal that. I actually just got this out of a Cisco document for sake of the visual. And again, you can also see here that there's a station count. So a lot of good information here in the beacon. Now we're going to focus a little bit about 802.11n beacons, and we could probably spend all day on this, but I just want to kind of point out a few things. One, you have the capability, the compatibility information field in the beacon, and you're going to find this also in 802.11ac. This is pretty much stations and access points will send this in their probe requests and their beacons, probe responses, association, reassociation. They're pretty much stating, hey, this is who I am. For HT 802.11n, and this is what I support. This is what I can operate on. Also, you're going to see whether or not it supports aggregate MPDU, and again, we're throwing out a lot of MPDUs and PSDUs. We're going to go through those here shortly in some later slides. And how many spatial streams that are supported. It's a lot of rich information. Before we looked at the compatibility, but we're also now here we're going to look at the operation. So what's the difference between compatibility and operation fields in a beacon? Well, the operation field is specific to the BSS. So let's say you have 100 access points deployed, and 99 of them are bonding at 40 megahertz, and this one isn't. Well, this is how this access point is able to share that information in its own beacon to the clients that may want to attach to it. So you're only going to find the operation information element in beacons and probe responses, I believe in association response. Again, only from the access point. So a lot of wealth of information there. Let's look at an 802.11ac. You're going to see the same thing here, compatibility and operation. We just learned compatibility is pretty much what the radios are capable of doing, and operation is pretty much what the BSS looks like. Are we bonding, what power sets, etc. Now let's look at some other important information that you're going to see. This is a null probe request. This is a probe request sent by a Proxim card. It's going out to anyone. It's going out on a channel. And I know it's a null probe request because there's no SSID there. Some access points are configured when they see this to respond with their SSID, and that's how you're able to build a neighbor list, or it's that list that pops up in the your Wi-Fi finder or your Wi-Fi supplicant. Now this, my friends, is a directed probe request, and you can see here, I know that because one, it's a probe request here, and I can see that there's a name. This is a network or a client that's actually trying to find a network called Fly Sacramento. If you've ever flown through Sacramento, that you'll notice that that's the name of their network. Now, this brings us to another question. I was posed this question a few times. And what's really interesting about this is that there's a ton of probe requests. You can see them with a lot of different names. Do you know when you take your laptop and you go home and it automatically connects to the home network, and then you take it to work, it all automatically connects to the work network? It's because it saves those names. And you can see those names here. It's for ease of use. Now, that's a beautiful thing, right? I mean, it just automatically works. However, there's a downside to that. I mean, there's tools like Karma that can be easily deployed on a Wi-Fi Pineapple. When your access point sends out these probe requests, the Pineapple will respond on behalf and will stand up a SSID and a network, and your laptop will automatically connect. And the Pineapple will give you an IP address, and now we have layer 3 functionality to your device. So it's very important. You're always aware of what network that you're attached to. And next, this is kind of the probe authentication and association flow. So you're going to see a client does a probe request. He comes back. There's a probe response. He does another probe request, some probe responses. And what he's actually doing, he's building a neighbor list. Based on the secret sauce on that client, he picks an access point. He does an authentication. There's an acknowledgement, meaning that the access point got it. There's another authentication that comes back. And then you have the association request, association response, and then we have our EAPs. This is where we're using 802.1x and we're passing our information. Now, what's important about the probe request is you're going to see that the probe request goes out. It's from my client, which happens to be an iPad 3, and it's broadcasted, saying, is anybody out there? This particular access point responds back with his information, and he says, hey, my network is 802.1x, WPA2, AES2. Again, that's just the name of the network that I have, and this is what I support. And then when the secret sauce kicks in for the client says, hey, you know what, I want to join you, specific access point. He then sends an authentication request. It's a very simple frame, not a lot of different information in it, but you're going to see here it's a management frame. It's also authentication. Then here you're going to see that we actually have another authentication frame. But what's really important that I look for is right here, the status code. It was successful. So the authentication request came from the client to the access point. The access point responded with, hey, we're kind of talking the same language. Our configuration looks pretty good. We're both using open system instead of shared system. Now, authentication on this level is not encryption. Keep that in mind. A lot of folks will actually misrepresent that. This is simply the jack plugging into the wall, so to speak. It's probably not the right term to call it authentication. But all this is just saying, hey, we're using open or shared, and if we match, we're successful. Next, what happens is the association request. So here we're looking at the association request, and what you can see in the association request is, again, I want to join you as an access point, and then the access point will respond if everything matches with a successful code. Again, very rich information. We had the authentication request, then we have the association response, or association request, association response. So in this slide here, we're actually looking at the EAP flow. I only have 2 or 3 slides on EAP, but I think it's very important and I want to share, depending on the flavor of EAP that you have. And EAP stands for Extensible Authentication Protocol. What you'll find with EAP is that there's many different flavors. You have EAP PEEP, EAP TLS, EAP TTLS, EAP LEAP, etc. With EAP PEEP, for example, you have approximately 15 to 25 different exchanges that go back and forth. One thing in particular that I wanted to share was the outer identity. You're going to notice that during the EAP process, one of the response frames asks for some information. You're going to see here on the Intel supplicant client, it's called the roaming identity. Some folks will actually put their external or AD credentials in here, not knowing what that really does. On the Windows native supplicant, you're going to see there's a checkbox called Enable Identity Privacy. And on the Cisco, or on the Apple supplicant, in this case, the how you can create the profiles, it's actually called Outer ID. What's important about this, and the reason why I have this one blacked out, is because this, whatever you put in this field, actually gets transmitted over the air, clear text. So in this particular case, this gentleman is actually sending his ID over the air for anyone to sniff. When I actually captured this frame, I had my own ID in this, and I didn't want to share that. So you're kind of giving up a little bit more of information about your network than you should. The other part that I want to mention here is, remember we talked about the group Cipher and the pairwise master key? When the client actually joins the access point, you're going to see the first part of the handshake. This is coming from the access point to the, or from the client, from the access point to the client. And this is the start of the process to create that unicast encryption key. The second exchange of the 4-way handshake is actually coming from the client back to the access point. These 2 frames actually complete the unicast encryption, or the Cipher encryption. The third part of the 4-way handshake is where the group key actually gets distributed from the access point to the client. This is how come he's able to use this key to encrypt his multicast and broadcast traffic. And the last key comes from the client back to the access point, pretty much simply stating, do you have all this set? Is everything installed right? Now, there's some other information in a frame that I think is very important that we're going to cover here quickly, is that we have the retry rate we talked about earlier. See that here? We have the to and from distribution. Believe it or not, if this was a data frame coming from the distribution, from the wired side, this bit would be flipped right here. And if it was coming or going to the distribution, the other frame would be flipped. So you can actually watch the traffic flow on where the frame's going wired side or not. Now, in this case, this is actually a control frame. So again, this is the traffic cop for 802.11. So what's important about that is the information that you're seeing here is that this frame never hits the wired side. So let's talk about control frames. I have a few control frames that we're going to go over. One is the RTS, request to send. Not a lot of information in this particular frame. There's no data payload. In fact, you can see our duration time. Again, we already learned what that is. And pretty much RTS is going to a radio, in this case a client to an access point, asking to reserve some time because it wants to send a transmission. The access point can respond back with a CTS, a clear to send. And again, he's also using the nav duration time to keep radios at bay so they won't talk over the transmission. And then we have acknowledgement. Acknowledgement is saying, I've sent you a frame, did you get it? And you as the receiver will acknowledge back that you received the frame. So again, not a lot of information, very simple frame here. And then we have block acknowledgement request and block acknowledgments. So block acknowledgements were part of the 802.11e standard, part of QoS. It's largely adopted in high throughput and very high throughput. It's where you can aggregate frames, where I can send multiple frames and not have to acknowledge each one individually. This is an improvement on the MAC layer to provide more bandwidth. So when you look at the block acknowledgement request, and then you look at the block acknowledgement, you're going to notice here, if you could read into these bits, it would actually comment as to what frames it was acknowledging. So if it sent 50 frames and I got 49 of them, for example, you would see that here in the bits. So polling question 2. How many of you think capturing and understanding how to interpret 802.11 frames could help you with your troubleshooting efforts? A, yes, I think so. B, no, I don't think so. Go ahead and register your vote. So let's move on to 802.11 data frames. A data frame is really simple. What you're looking at here is actually an encrypted frame. So we have our normal packet header information, our MAC header information, and then we have the encrypted payload. Now you're going to notice that we can't see anything inside the payload itself. However, if you had an unencrypted network, for example, let's say a guest network, where you weren't providing any type of encryption, and you were to sniff a frame, you can easily see a lot of information. You can see the IP address source, the destination, the ports being used. So a wealth of information can be garnered from an unencrypted network. The other part that I want to mention is the data null frame. I mentioned this. This is actually a data frame. You can see here, it's a data frame. The subtype is null, but there's no payload. The purpose of this frame is for this bit, power management. This is an indication to the access point to either buffer frames when it's set to 1 or not. It will send another frame at 0 to say, hey, I'm back on channel. Go ahead and send any buffer frames that you might have for me. So now, moving on to topic 2, LLC, MAC, PLC, PMD. And I have to tell you, this is really good information. I am fascinated about how a packet can move through the network, then become a frame, and then get modulated into bits. Fascinating information here. So put on your thinking cap with me. First off, we need to understand the layers. Layer 2, we have LLC, Logical Link Control. That is a sublayer of Layer 2. And then the other sublayer in Layer 2 is MAC, Media Access Control. Then we get down to Layer 1. We have PLCP, Physical Layer Convergence Procedure. And then we have PMD, Physical Medium Dependent. So what exactly goes on in these layers? So a packet is also referenced as an MSDU, a MAC Service Data Unit. We actually reference that as a packet at that point. A lot of folks often confuse packets and frames. But at this point in time, this is called a packet. When the upper layer is handed off to LLC, LLC hands it off to MAC. MAC then encapsulates the MSDU. It's now called an MPDU, a MAC Protocol Data Unit. And this, my friends, is when we call it a frame. After this encapsulation, the MAC sublayer sends it down to the PLCP layer. At this layer, it gets encapsulated again into PSDU and into a PPDU. At this layer, the PHY header and preambles are added. And then it gets handed down to PMD, the physical media dependent layer. This is the layer where it gets modulated into bits. So let's look at this, and this is from the CWNP, CWAP book. This is showing data going down the network and then data going up the network. So a quick caption, you have an MSEU going down the network that's delivered to the LLC. LLC delivers it to the MAC layer, encapsulates it. It's now called an MPDU, and you're going to see that the MAC header and trailer are added. So this is where your MAC address gets added to the frame. And then gets handed down to our PLCP, which again is encapsulated here. And this is where our preamble and, as I mentioned, PHY header are added or removed depending which way we go up and down. Now what's very important and very interesting is this piece, the bits. How do we send bits over the air? Right? I mean, that's really, really interesting, and I was absolutely fascinated when I started learning about it. So let's spend a few minutes and talk about bits. So here we have a spectrum mask. Now think of a spectrum mask as a highway. The one on the left here is direct sequence sped spectrum, and the one on the right is OFDM. The one on the left, think of a 2-lane highway. The one on the right, OFDM, think as a 10-lane highway. Now, how many cars you can put on that highway is important. So in direct sequence, we can only put so many cars on that highway, and we have different modulations. Now, think of modulations as cars and buses. So if I have one modulation, which happens to be differential binary phase shift keying at 1 phi, for example, I'm only putting 1 or 2 people in a car. Now, if I can double that, and now we start carpooling, I do differential quadrature phase shift keying, I've doubled your bandwidth. So as we get more and more as we use more and more complicated modulations, we can put more cars on this road. So we have the modulation ERP OFDM 802.11g. It's almost identical to regular OFDM on 802.11a with a few differences, one being the protection mechanism that's required for backward compatibility. But you're going to see that we have much more complex modulations. We have binary phase shift keying, we have quadrature phase shift keying, quadrature amplitude modulation at 16, quadrature amplitude modulation at 64. And you're going to see we have the same for A. Now in this slide, and what I want to draw your focus to is again the modulations. 802.11 HT is using complex modulations, again 64 and different spatials. 802.11ac, very similar, but you're going to notice that we jump from 64 modulation to 256 QAM. So really, what does all that mean? How do we move bits from one radio to another? Well, let's start back from the very beginning. It's almost like sending smoke signals. In binary phase shift keying, I'm sending 1 bit per modulation. And friends, this is a modulation right here, from here to here. In this particular case, this modulation or symbol, right here, symbol is data, is at 180-degree phase. Out of a pi of a 360, this means I have 2 waveforms, or I have 2 phases. And these, my friends, are the 2 phases. So if I were to send a signal in this form, in this phase, it represents a 0 at the receiving radio. If I send a signal or phase, radio transmission, in this phase, right here, in this waveform, it represents a 1. Very simple, 0s and 1s. Again, it's like sending smoke signals. Then we have this thing called a constellation. There's some complicated methods behind this, but if I send this waveform, it meets this particular constellation, which could be a 0, and if I send this waveform, it meets a 1. So very simple. I'm hitting constellations here. Now, if I were to do much more complex modulations, let's say instead of sending 1 bit per waveform, let's say I send 2 bits per waveform. Now I've just doubled your throughput, right? So that's what quadrature phase shift keying does. It actually uses 2 bits per modulation symbol at 90-degree phases. Now again, 90-degree phases times 4 is 360. So this gives us 4 waveforms or 4 phases. So if I were to send a signal in this fashion, it means 0, 0. If I send a signal in this fashion, it means 0, 1. If I send a signal in this fashion, it's 1, 0, and then, of course, 1, 1. Now, this, depending on the phase, will register to a constellation. Now, there is an error here. You see 0, 1, 1, 1, 0, 0. This actually should be 1, 0. There's a typo there. Now, let's add to the complexity. So we just took 1 bit. Now we're taking 2 bits. Now let's look at quadrature amplitude modulation 64. Now we're going to add 6 bits per symbol. Now what's very important about this piece here is the quadrature amplitude modulation. Let's step back. If I were to able to take this signal and I were able to increase the amplitude or decrease the amplitude in a manner, and then also take the phase, which is from here to here, and change that slightly, I can match one of these constellations. What does that mean? Now I'm sending even more bits. I went from 2 to 4, or 1 to 2 to 6 bits. And you can see here that if I send a phase and amplituded waveform, and it matches this constellation, that means it represents 1, 1, 0, 0. So a lot of good information there. So what happens when we get to 256? This is where we're sending 8 bits per symbol. And again, same thing. You're going to notice that our bits here are a lot more defined. We have a lot more bits to hit. And this is the reason why, if you look at Cisco or other 802.11ac access points, the transmission power has changed. We're no longer at 100 milliwatts. We're at 200 milliwatts. So I need to make sure my transmission is so clean so the receiving end can hear those little drops and increases in amplitude and the phase to meet one of these constellations. And if it does, it knows what bits it sent. So as we work down the chain from a packet down to a frame and then to bits, this is where the rubber meets the road for the bits. So how do you test something like this, right? So let's look at this. Here's a great example. What you're looking at here is quadrature phase shift gain. I know this because we actually have the 4 areas. Now, when a transmission leaves, or when a signal leaves the transmission radio, it's never always heard exactly how it was transmitted. You have a noise floor. So again, it's like somebody whispering in your ear, and you didn't necessarily hear the entire conversation. But let's just say I'm in this general vicinity, which a lot of these dots are. Then I know that you represent, in this case, 0, 1. But now let's assume this is an SNR of 10. Let's assume an SNR of 6. That means lower signal or higher noise floor or both. What you're going to see here is that it's not necessarily clean. You're not necessarily hitting the right constellation. So now your bit error rate increases. Now, another example of that, you can look here, which is, again, 16 QAM. If you look, there's actually 4 dots in each section. So that's 4, 8, and then 16. Same process is going on. And last but not least, and that will sum up the waveform. So hopefully folks will now understand how bits get transmitted over the air. And last but not least, I want to talk about 802.11ac frame captures and our deployment of the Cisco 3700i in our all-wireless office. So real quick, we have approximately about 400 wireless users. There are no cable drops. This is not an office where we did cable drops and, oh, by the way, just use Wi-Fi. That's not the case. There are no cable drops. The cable drops that are in this office are for printers and for conference room phones. That is it. We do 24-hour, 7-day-a-week traces with wild packets from 3,700 access points in Sniffer mode. We used Air Magnet, Wi-Fi Analyzer, and Survey to ensure that our deployment was good. And something else I want to mention, we're working very closely with Intel on our drivers. We had a lot of issues when we deployed. We identified some of those issues to be Intel driver issues. And I have to tell you, the folks that I'm working with, Eileen and John, have been absolutely helpful in our success. In fact, we've gone from 10 to 12 drops a day per user, fine-tuning the infrastructure, RRM, session timeout, user idle timeout, and channels. We got it down to 5 and 6 drops a day. What we noticed was that the Intel driver was sending some random DOFs, working with Intel, providing them our packet traces and tools that they provided us, and sending all this information back to John and Eileen. They were able to get us a driver fix. So we're on a beta driver. We did some extensive testing with it. And now our users, we have about 10 test users, and they're reporting anywhere between 1 to 2 drops a week. Now, these are guys that are really strongly relying on Wi-Fi. It has to be reliable. So we're we're collecting so much rich information from this that it's absolutely helpful for our larger deployments and how we assess our enterprise from a distribution level of wireless. And this was really a slide that I just want to kind of point your attention to are these green lines here. This is actually 802.11g, 802.11n, and 802.11ac on a MacBook Air 2x2 with 2 spatials. You're going to see right under an access point, you can't even really see the throughput, but really we're pushing about 8, 9, 10, 12 megabits per second. 802.11n, same access point, right under it, you can see we're roughly about 200 megabits. And then with 802.11ac, just 2 waves on the MacBook Air, you can see we're at 400 megabits. This was one of our selling slides to management to say, hey, you know, we're close to a replacement for the wired, and you know, they gave us an opportunity to do the all wireless office, and it's going very well. And I believe this is my last slide. I'm often asked, well, how do you throw an access point in the Sniffer mode? It's real simple. You go from the local mode, drop it in the Sniffer, then you go into the individual access point. You select the channel you want to sniff, and then you select the packet capture utility that you want to send it to. There are a few things that you want to be aware of. We have a number of access points in Sniffer mode, and some actually stop sending traces after a period of time. So we actually have to go in and we have to toggle this little Sniffer button, and all of a sudden it starts up again. I believe this is related to a bug that's fixed in 8.0. And also we're noticing that it displays a normal amount of CRCs. So when you start to go through the packet capture, you're going to see a lot of CRCs capturing 802.11ac frames from the access point. Also notice that's on Aruba as well. We've worked with OmniPeak. Jay over at Wild Packages is great. Wealth of information, and working with him on this to see if whether or not it's an OmniPeak issue or perhaps a radio issue. And that's pretty much all that I have. Thank you.
Thank you very much, George. Great presentation. I also want to thank everyone for participating in the event polling. And now it's time to answer some of the questions our viewers have submitted today. And if you can't stay with us for the Q&A, please be sure to click on the evaluation link provided in the chat to let us know how this session met your business needs and expectations. So we'll get to some of the questions right now. George, we have a question on any medical equipment supporting 802.11b?
Yeah, you know, So try to avoid that like the plague. You know, 802.11b, obviously a much slower modulation. You have to accommodate that. It will literally throttle your network. Devin Aiken has a great white paper. It's called The Ripple Effect. Every time that you add an 802.11b client to your network, backwards compatibility has to work from 802.11g, and it throttles the network down. Now, from a medical device perspective, we've been very, very successful with our biomed department, and I can't say a lot of places have been. But again, we evaluate and we educate our biomed folks why we can't bring in certain devices. And we've recently tested actually an 802.11b device, and I have to tell you, it wasn't easy to, or it was rather easy to share with biomed why we didn't want it on the network. And they had the faith in our abilities and said, you know what, we're not going to move forward with that particular product. And now the vendor actually is rethinking their deployment because they're going to lose out on an opportunity with Methodist. But try to avoid 802.11b where you can.
All right. Thank you very much, George. Another question here on QoS data null frames confuses me. What are the purpose of those?
Yeah, so the QoS frames for data, it just simply means that the client is negotiating and supporting QoS. So really, if you have QoS implemented and your client that attaches is QoS capable, your frames will be marked as QoS data frames. If you attach a client that is not QoS capable, it will just simply send simple data frames and not with the QoS header. That's really about it.
Okay, and this is in reference to, I think, some screenshots previously. They were asking if the screenshots are from ICE or Prime.
I'm not sure what screenshots they're referring to. The screenshots that I have here that I've shared are out of the Cisco wireless LAN controller. So where I had the insets in some of the earlier slides were from there, and all the other slides have largely come from OmniPeak itself.
Thank you. And from which tools are coming the screenshots displayed in the slides? And I think you just discussed a little bit of that.
Yeah, again, I'm a big fan when it comes to the deep packet inspection with OmniPeak Wild Packets. I think they do a great job, and the team over at Wild Packets, working very closely with those guys, because there's things that I see that just pop up that aren't right. I email them, and I get an email back like in minutes. So enjoy their products. But we also do use Air Magnet and their survey and Wi-Fi analyzer from a design perspective. So again, very rich tools. They all have a specific need.
Okay, and this is another reference to the tool. What tool showed the whole connection flow with bars and max and such?
Yeah, again, this is the OmniPeak. There are other means to capture frames. You could use Wireshark in a Linux flavor or load backtrack. So Wireshark is very popular. It's free. However, I'm more familiar with OmniPeak. It's just I can build a lot more graphs and compass and different information. I can pull it out quicker than I could on a Wireshark.
Okay. And is the multicast broadcast group comp shared key handed out by the app? If so, by what mechanism?
It's actually handed out by the access point. So, for example, when the client joins the access point through the association phase, the key is already on the access point. And during that association process, and it goes into the RSN information element or WPA information element, the key is then pushed to the client, at which time the client then takes that key and then quote-unquote installs it. However, that is configurable. If you go into an autonomous access point, you can rotate those keys by time, I believe, or even by transmission. If you send 1 million frames, then change it. And then also in newer code, you're going to see the GTK key option, GTK. And from there, then you can actually change how often you want to rotate that key.
Thank you. And this is a little bit more of a lengthy question, so feel free to expand on it. What does the entire packet capture look like, and how much digging through individual packets you need to do to get to this information? In other words, for these few slides, how many packets did you need to dig through?
When I guess I'm basing this question on when I'm trying to troubleshoot an issue. I've studied what a perfect network looks like. I understand how the probe requests and probe responses work, authentication response, all those. And when you work on a network or on a device that doesn't behave properly, it kind of sticks out like a sore thumb. So when I go through and here it's very important to mention that you don't necessarily bring out the sniffer as soon as there's a problem, right? You go through your basic troubleshooting. You might look at prime, you might look at the client configuration, you might look at debugs, you're going to look at logs, you're going to go through the GUI. But when you're still scratching your head, bring out the sniffer and sniff it. Usually within a few frames, and again, the frames are going by very fast, but usually within a few frames, you can start to see a pattern. And if the pattern doesn't look normal, then it starts to draw your focus into what is abnormal. I hope that helps.
Great explanation. Somebody asked, what was the white paper name, the ripple effect?
Yeah, Devin Aiken, ripple effect. If you just Google that, you'll find that out on Google. It's by Devin Aiken. It's called I believe it's called the 802.11b ripple effect. But Devin Aiken, ripple effect. I'm sure it'll come up.
Great. And here's a question about what do you think about Wireshark for Sniffer?
I think it's a good tool. It's free. Because of the Windows, you can't necessarily use it on Windows unless you're going to use the special adapters from AirPCAP. But if you're familiar with Linux, certainly you can load your driver, turn on your captures, and certainly use Wireshark. Wireshark is very rich. There's no, really don't have an opinion other than it's a free utility. It's very rich if you know how to use it.
Thank you. And how are you finding 802.11ac AP deployment different from 802.11n?
Yeah, I've been asked that question a lot. From a deployment strategy, and again, this is my opinion, and I'm sure everyone has their opinion if they do Wi-Fi deployments. I'm finding that they are a direct replacement for 802.11n access points as far as the cell coverage is concerned. Also, the higher transmission rate allows us to send more bits. If you go back and look at those constellations we talked about, and that's why you're seeing the higher transmission powers. However, we're still designing for the lower common client. So, if I have my client that's, 25 milliwatt, you still want to design for 25 milliwatt. However, if that client is closer to the access point, they can pick up in power, change the amplitude and modulation slightly, where now you can send more bits. So for me, the deployment is still a one-for-one. The bigger challenge for 802.11ac and deployment-wise is how do you sniff these frames? Fluke just recently mentioned at the recent Tech Field Day that they're coming out with a special adapter. But in order to sniff 802.11ac frames beyond two spatials, you need to actually use the access point at this point. So that's changing how, as a network engineer, how you operate, right? You can't carry around an access point in your bag necessarily. So there's some challenges there, and I think those are going to get worked out over time.
And what steps were taken before implementing 802.11ac?
Wow. First was to get the okay from management, right? Because this is a big undertaking. When you take a couple hundred employees and say, hey, you're going to be on Wi-Fi and you're going to like it, right? So it was a matter of showing them our game plan. We're going to do an active survey. We're going to make sure we cover every square inch. We're going to make sure we deploy the network with best practices. We look at our deployment strategy, and we start then testing, and we start to realize we have some driver issues. We then go back to the packet captures. We look at where the problem lies, and then we get all the players involved. For example, we get Intel involved, we get Cisco involved. Working with Mark Denny and Javier have been strategic to our success in the all-wireless office. So it's really partnering with folks. And we recently partnered with Lenovo, talking about their new card, the Intel 7265 card that's coming out. So we're looking to leverage that in our all-wireless office. So a lot of partnering going on, a lot of boots on the ground, a lot of customer-facing. Methodist has a wireless team of 4 folks. And if you look at other institutions, it's usually the route and switch guy. Oh no, by the way, he does wireless. So we do a lot of customer facing, and the team that I have, all 3, including myself, but the 3 folks that I have all desktop experience. Great customer facing skills, great troubleshooting skills. They know how to navigate the operating system. So when you put them out in front of users, I mean, think about this. When was the last time a routing and switching guy, or for that matter, a security guy, ever have to talk to an end user? Very rarely happens. Wireless, it happens regularly. So, we have very well-versed engineers in the field handling this. And when you have that all-wireless office, that's what you want. You want to have very well professional folks dealing with doctors and clinicians in such a manner that you can get to the problem and resolve quickly.
And as we deploy 2.4 AP radios closer for throughput, could you explain the best tools to determine CCI issues? We are using Cisco 3600.
Yeah, so I have to kind of read between the line with that one. I'm believing that he's probably saying CCA, maybe, the co-channel contention or clear channel assessment. But so on 2.4, now here's my stance on that. I personally believe 2.4 is a legacy protocol. In fact, we're rolling out a 5 gigahertz only network. I would strongly consider making sure all of your designs are 5 gigahertz, deploy SSIDs or wireless networks that only support 5 gigahertz. Don't do 2.4 and 5 gigahertz, and give the client the option to choose which frequency to go to. A lot more beneficial to your operation as a whole, more channels to select from, less interference, less co-channel contention. If you have 2.4, and you start to add density, you're going to have a lot of chatter going on.
Okay, thank you. And how many clients can be accommodated on 802.11ac AP simultaneously using media-rich application? Wow,
that's a great question. First off, I'm not a marketing guy. I'm an engineer like probably most of you are. I'm not buying into all the bandwidth that VC actually plays a part in. If I were to give you an 802.11ac access point laptop today, you're probably not going to do anything differently than you did yesterday with your 802.11n or 802.11a device, right? You're still going to do the same workflow. The real value, in my mind, with 802.11ac is that I can trigger a frame on and off the network faster than I ever could before, which allows the media to be free for other devices. So the question is on a rich media environment. Now, I can tell you that we've gotten up to 30 phone conversations over a single access point. Once we got into 32 or 33, we started to break. The quality started there was a lot of jitter. And again, these are access points with phone calls going to other phone calls on that access point with Cisco 7925 phones. So it's pretty impressive from a phone perspective. From a rich data perspective, I can't say I actually ever tested that piece yet.
Thank you. And here's a question from somebody in a similar situation to you. From a hospital vertical and struggle, they work in a hospital and they struggle with numerous devices. Do you have a procedure or recommended process for device testing? I found your intro really resonated with me in some of my trials and tribulations in Michigan.
Yeah, I feel your concern, especially if you're in healthcare. First and foremost, you really need to partner with the facilities, security, and biomed. That's really where you start to control the faucet, so to speak. Once you can kind of control the faucet, educate those guys. Try not to be a roadblock. Try to work with them and understand and share with them why you need to test the device and why it may fail. Even to the point of doing packet captures and sharing. They may not know all the language, but at least they'll know the bits and pieces of what you're telling them. And then it's working with vendors. I can tell you that we've had a lot of successes, and a lot of them recently, working with GE and Philips and some other providers, and sharing with them, hey, you know what, your neck gear is not going to cut it, and this is why. We've gotten sick and tired of hearing it's our network time and time again. Well, guess what? Come on out. Let me show you. And I can tell you, when they leave Houston Methodist, they're more educated on frames than they've ever been. And they typically will raise the white flag and submit. Then it's a matter of what can we do to fix it. So we go through a lot of testing in a sense of we look at a device, we see it associate to the network. If we're using 802.1x on that device, is it operating appropriately? Is it authenticating appropriately? What does it support? Does it support opportunistic key caching? Or every time does that device move from access point to access point, does it need to do a full 802.1 auth, thus delaying perhaps or causing some roaming issues? We also look at interference. You have a jammer. You turn a jammer on, break that connection with that 2.4 device, for example, or that 5 gigahertz device. Does it automatically reconnect on its own? If it doesn't, then we know that before we deploy it. We know that if there's interference and if there's a certain level of interference, that somebody's going to have to go out and manually touch that. We're not going to get a phone call later on and say, hey, by the way, we lost all these clients because there was some interference. Or maybe it does automatically reconnect. Right? So there's a list of about 40 things that we go through, and we kind of checkbox and note. Does it support this? How did it operate here? What did it do when we did this? And that's an internal list that we use, and it continues to grow as we start to see more and more devices come in.
Thank you. And what have been your biggest BYOD challenges? If you have Intel issues, you have to troubleshoot. How do you approach having to troubleshoot Android and Apple?
Yeah, so BYOD, we actually have ICE. We did that earlier slide of all that infrastructure. We do everything in-house. We do our own designs, our own configurations, our own deployments, and own troubleshooting, including ICE. We were a very early adopter to ICE for BYOD. The challenges are many, especially when you start to work with Apple devices. They don't necessarily behave right. Let me give you a quick example. If you have an SSID that you've had for years and you want to support the FT, Fast Transition 802.11r roaming, and you simply just checkbox that on there, what we found is that we actually lost some legacy devices. That information element in the packets or in the frames, some devices didn't like to see it, and they dropped off. So we realized that, probably to facilitate Apple roaming, we need to create that new SSID. In this case, that's our 5 gigahertz SSID. So all of our business machines are moving over to 5 gigahertz where we'll have FT enabled, and we're going to test our business machines before we deploy them to make sure that they support FT. But again, very challenging environment.
And regarding all the QoS, does that need to be implemented on the wired side?
Yes. So when you start to talk about QoS, it's a complicated subject. You have QoS on the wireless, and then you have QoS on the wired. Let's talk briefly on the QoS on the wireless side. So you have a station or a device that not only from an application level has to mark the packet for QoS, the NIC has to honor that. And really what that does is it creates a smaller contention window. It means it gives it a higher probability for that frame to transmit over the air than, let's say, a device that doesn't have QoS. So there are contention windows that come into play. If for some reason the device doesn't support QoS, it could be lumped in that bucket of same contention windows as other devices, and now it has fair game of trying to get to over the wireless medium. But once that packet hits the wired side, especially at the wireless LAN controller for unified, at that point you can use AVC to mark it up or put policy maps then in place. But yes, ideally you want to have QoS throughout upstream and downstream. And it's very important, and packet captures are critical to that because you can actually see whether or not the client is marking their packets for QoS and taking advantage of the smaller contention windows.
And we have another question here on what are your experience with RxSOP, and can you share some info about real-life use? The person who asked the question is using it in HDX environments, but I want to hear another opinion about this.
Yeah, wow. So RxSOP isn't anything new necessarily. I mean, if you did early 1300 and 1400 bridges, you can actually change that receive sensitivity. Now, why is this important? Well, for years we've used signal as a form of how loud a cell is. So if you're transmitting at 100 milliwatt, you have a cell at a certain size. If you transmit at 50 milliwatt, your cell size is much smaller. But that doesn't necessarily prevent you from what you're hearing. So if you look at the receive sensitivity specs, and Cisco publishes these, of a radio, you can see how well a frame is, how well that access point hears. And access points hear relatively very well. So they're listening, again, it's like a CB radio. If you're on channel 1, it's listening to all those frames that are in earshot of that receive sensitivity level. Now, if I can take the receive sensitivity level, and let's just say the access point's at -85, and maybe move it to -80, I'm no longer hearing those neighboring cell transmissions that necessarily I may not necessarily want to hear. That could cause me to back off, meaning the access point. But you want to use RxSOP very carefully. You can obviously see the results. If you tune down RxSOP, you're going to see channel utilization goes lower. But if you don't have a proper design and that client is at the cell edge, and maybe he's at that -80, and again, not a proper design, but let's say he's at that -80, when he triggers that frame, the access point's going to drop it when he hears it. He's going to say, oh, I'm not supposed to listen to you, drop. So you want to be very, very careful with RxSOP. You should have a solid understanding of RxSOP, lab it before you deploy it, and make sure before you start tweaking those knobs, understand if you have the proper design to support it.
Thank you. And we have some time for just a few more questions. So the next one is, what different test cases should you run for pre-production deployment for 802.11ac?
Can you say that one more time?
Sure. What different test cases should they run for pre-production deployment for 802.11ac?
Test cases. So really, I think is understand one, what is the need, right? What is the need for 802.11ac? Obviously, all the chip manufacturers are going to be producing 802.11ac going forward. So whether or not you want AC or not, you're probably going to get it, right? Because that's what all the new access points are going to have. You don't necessarily want to buy old gear. You always want to stay up with the newer technology. So specific test cases, in my opinion, again, this is my opinion, the site survey hasn't really changed a whole lot. If you're familiar with site survey, by deploying 802.11ac doesn't necessarily change that. Now, if you're in an extremely high-dense environment, 802.11ac is certainly going to help with that. You're going to be able to get more stations, more airtime to transmit. So where does that come into a use case? Well, in cafeterias and in conference rooms, I would do a study before 802.11ac, and then with specific traffic characteristics and then do a study afterwards with 802.11ac. And again, just because you have AC doesn't necessarily mean it's always going to provide the higher rates, right? So you need to make sure clients are supporting it. And clients are now just coming onto the network with 802.11ac. You look at the new Macs, and you look at the Android devices from a mobile perspective, they're all coming with 802.11ac devices. Our new Lenovo's have the 7260s. They're coming out with 7265s here shortly. So now you're going to start to see over time, more clients transmitting data quicker. So, when you start to try to figure out where the need is for that, it comes down to what's your opinion of, or what's your strategy for 802.11ac, really.
And a couple people had asked if you could share your checklists that you had mentioned. Perhaps you can share that on the community?
I'd be glad to, absolutely.
Okay, so the users who wrote in on that, you can go ahead and reference the Cisco support community, and George will post it up there. And this is we have time for one last question. Are there any bad experiences regarding virtual wireless controller in productive environment, where you're planning a guest network with one VWLC and an ISE?
I wish I had that experience. I only run the virtual controller in the lab, so maybe Nicola or someone else can comment on that. But unfortunately, I don't use the virtual controller in production.
All right. Well, thank you very much for answering all the questions. That's going to conclude the Q&A portion of today's event. And now for our trivia question. What does our Cisco VIP George and Houston Methodist Hospital share in common? And you can take a moment to answer that question, and we'll answer it a little later in the broadcast. So we're going to review some upcoming webcasts. On September 16th, there's a webcast on Cisco UCS Unified Computing System, UCS B Series Upgrade and Troubleshooting. And on September 22nd, a webcast on ESA Configuration and Troubleshooting Training. So you can register for those at the links provided in the chat window. We also have an upcoming webcast in Portuguese on Cisco Fabric Path Overview, Unraveling the Protocol, and that takes place on September 3rd. We also have some upcoming Ask the Expert discussions. The first one is Overview Cisco Prime Service Catalog and Process Orchestrator Solutions. And the second one is on enterprise design and deployment of multicast solutions. Those both start on September 1st and last through September 12th. If you haven't already logged into the Cisco support community, we encourage you to do so. We have a brand new look and feel, so log in and start sharing today. And of course, be sure to join the Cisco support community where you can share current real-world technical support knowledge with your peers and experts. You can also participate in live interactive events. Check out the Class of 2014 Event Top Contributors and Spotlight Awards on the Cisco support community. If you're interested in conducting an event for us and becoming a top event contributor yourself, please go to the Experts Bureau and sign up. Our presence in social media keeps expanding, so we encourage you to visit the community and join us through the various channels. We continue to expand our reach in many different languages. We have also recently launched our Chinese community, so please be sure to stop by and browse through it if you speak Chinese. Take a moment to rate the content of your peers' documents, videos, and blogs. In doing so, you help us recognize the wonderful content that they contribute. Looking for more information on IT and technical training, you can log into the Cisco Learning Network and take advantage of the technical webinars that they offer, and go to the link provided in the chat to learn more. And we have a couple of programs that may be of interest to you or someone you know. So if you are interested, you can go to the link on your screen or in the chat window to find out more information. The first program is Cisco Entrepreneurs in Residence. Cisco EIR fosters open innovation at Cisco by forging connections with the startup community. Cisco EIR is looking for early-stage entrepreneurs building next-generation products. They are currently accepting applications for the fall class. And the second program is for coders out there. There's a series of ongoing developer challenges hosted by Cisco and Top Coder. So you can join our online innovation challenges on Top Coder and get rewarded. And now the answer to the trivia question. George and his team of wireless architects evaluated 3 to 4 new wireless-based specialized devices for Houston Methodist Hospital. All wireless bedside use was made possible by 802.11ac radio module for high bandwidth and high density wireless locations, allowing a faster and more convenient way for diagnosis and treatment plans. So if you selected B, you had the correct answer. Before signing off, please take a few minutes to complete your evaluation of today's session. This will help us address your business needs and interests in the future. And this concludes our session today. I want to thank George Stefanick for sharing his expertise with us today. Really great presentation. And I also want to thank experts Nicola Darsha and Bernardo Gaspar for answering your technical questions. And I want to thank you all and have a wonderful day.